Live stream. Okay. Okay. So in the last discussion, we saw basic things about what is an abstract data type, what is a data structure, and we saw complexity analysis, right? Those were the basic concepts which one has to be aware of if you want to write good programs. Now let me open I have shared my screen with my writing pad, and I will also open the a Jupyter notebook so that we can also do programming here. Okay. Okay. Let's take up a topic called arrays today. Actually, we are looking at linear ADTs, which means linear data types. And we have what we are going to discuss are arrays. So what are arrays? Arrays basically, if you know Python, it's a list. A list is a kind of array. If I say list A is something 2, 5, 7, 1, -1, etc. This is an array, right? Which basically means it's a linear data structure where you are saving your information. So it has two things. One is the index, right? So let me write the index. Index will be, this will have 0, 1, 2, 3, 4. So this is the index, and this is the data, the actual data. If I ask you what is the data kept at index 0, it is 2. Data kept at index 1, it is 5. And this data need not be integer, right? It could be strings also. Let's say I have another array, this is A1, another array, which is apple, comma, boy, comma, cat, right? This is another array, and the indexing is still same, 0, 1, 2. So if I want to ask what is the data kept at index 1, it should return a boy. Now there are two kinds of arrays. One are the static arrays, and other are the dynamic arrays. What are static arrays? They are constant in their size. What are dynamic arrays? They are dynamic in their size, which means their size can change. Let's say it is a class of 50 students, and you want to save their marks. What are the marks in the mid-sem exam and sem exam, etc. So you can create a static array, and it has let's say index from 0 to 49, and you will say, okay, at for this particular index number, save this much marks for the mid-sem, and then another array of end-sem marks that will also be. But let's say if the number of students is not constant, there are always new students getting added and old students, they are dropping the course, then it will be kind of dynamic array, right? Because the size of the array is not constant. Size is changing with time. So Okay, let's look at static arrays first. In the static array, what are the functions possible? What functions would you like to do? Let's say take number 1 static array. What all functions would you define here, or would you like to use? One function is access. An example is what is the data at index 5, right? This is called access. You want to access the data which is stored at a known index, right? This is called access. Another function could be search. I ask you, is this data present in this array? For example, look at this array which we have drawn here: apple, boy, and cat. I can ask, is the entry boy there in this array, or is the entry girl there in this array? The answer will be false. No, it does not contain any girl entry. And if the entry is there, let's say boy, is the entry there? It will say yes. Then I can ask, okay, tell me the index of that entry. So it will return. So I will write here. Yes. Return the entry or return the index. If the entry is there, then give me the index. This is a kind of, these are the kinds of functions which one may like to make in a static array, right? Okay. Can you tell me how do you do it in Python? Let's say you want to access the data at a particular index. What will you use in Python?
So square brackets.
Yes.
And right index.
Yeah, you will simply say a square bracket 5. Right? Index 5. Indexing starts from 0. And now, how about search? How will you do search in Python?
So we can
loop
use
at index.
we can do
Yeah, you can either use a loop, right? You can loop through all the entries, and you can say, okay, should I share my program? That may be better. Just a moment. Let me open my Jupyter notebook and share it with you. Can you see my screen? Can you see my screen?
Yes.
Okay.
Yes.
Thank you. So let's say you have an array A, which is apple, boy, and cat, right? And I want to access what is my A at 2. So what's the answer?
Boy.
Cat. Now I want to find does. Okay, let me. Oops, what did I do? So now find girl in this. How will I find girl in this? I will say, I can make a for loop for item in A if item sorry. This is a bad practice. I should always make a function, right? Let me say function, right? Function find or search an entry called girl. Okay, so let me make it in this way. So first of all, when I want to define a data structure, I should always make a class. That is a good practice. Class, let me call it as some array or linear something, linear list. And then I will say here, I want to put some entries in this init. And self is a standard default keyword, so don't worry about it. It basically means you are referring to the content of the whole data structure or the class. Self, comma, and here now you will write nothing, no problem. And then here you can say my A is this. That's it. And now you can define your functions here. Find search, self, comma, item, or target item, some target item. Item equal to target, then return true. And if this happens, then that's all right. And if after looping through the entire thing, it is still not there, then you can say return false. Right? Does that make sense? Now I can say here, let me define, oh, I did a mistake here, self.a. Because A is an entry which is associated with the class. A is the content of this class. Okay, now it makes sense. Now I will say here, let me define a list. Let me call it as A equal to linear list. Okay, then I will say a dot search girl. It returns false. Right? Does that make sense?
Yes.
And if I say a dot boy, what will it return? True. Okay, let's say I want to return the index of the item. I also want to return the index. Instead of saying just true or false, I want to return the index also. And then what will I use? I will have to say for, instead of saying for item in self.data, there are two ways. I can either do, okay, let me use the simple method instead of confusing you. There are some inbuilt functions which I am not using. Let's say I will say for I, some index I in range length of self.data, right? I'm going 0, 1, 2, 3. I is the index now. Now item equal to self.data I, right? If item equal to basically I can also do like this. To define extra words. If self.data I is equal to target, then return I. And generally, if you don't find it, then return -1. -1 means you didn't find it. Okay. Now see how things. Now it returns 1. At index 1, you have boy. And if I put girl here, then it returns -1, which means it did not find a girl there. Did you get it? Anybody has any questions in this simple data structure?
Sir,
Yeah.
sir, why is it necessary to define everything within this class?
Why is everything necessary?
To define within the class.
To define within the class. Okay. So this class is you can assume it's a bigger container, and it has data as well as functions to operate upon this data or access this data. Right?
Okay.
And it's a static, actually, I can call it as a static array. It's a static array, right?
Mm-hmm. Sir, while accessing that function,
Yeah.
can we write self.a.search? Is it necessary?
Here.
Yes.
No, you already have A available to you. A is available. But inside, let's say I'm in this function.
Mm-hmm.
Now I want to check every entry of data. If I write here data, right?
Okay.
Which data is this? Right? This.
Yes,
so the scope of a variable generally is within a function.
Yes.
Right? The scope of a variable is within a function. Do you understand the concept of scope?
Yes, sir.
So scope means this variable, if you set some value to this variable, that value will not be visible outside the function. Yeah. So let's say if I say here data, then what data is this? There is no variable called data in this function. So that's why everything associated with this class or this instance will be there in the self keyword.
Okay.
So if you want to access data, you will say self.data.
Okay.
And when here you set self.data, you are putting this data into this class, or basically into this container.
Self.
That's why you use self for within the class communication.
Okay. In case we don't use self, is there any problem?
If you don't use self, then yes, there is all problem. Then what is data here?
No, while defining the data set, while defining, yes, here if
I remove data, then this data will be just once you exit this function, this data will be destroyed. The scope is destroyed. Scope is finished, so the data will not be visible outside.
Okay.
Right? But this self is something which will be visible throughout this class. Self will be visible. So therefore, you associate this data with the self keyword. Now, this data is visible throughout this class. And to access this data, you just use self.data.
Okay, thank you.
Yeah, so self is basically a keyword which is available throughout this class. Okay, thank you very much for good.
Hello, sir.
Yeah.
So if we use self, then the scope is within the entire class. And if we don't use self, then how do we know that where the scope is like ending?
Within that function.
Okay.
Yeah. There are some other little bit more complicated rules, but yeah, mostly that's how it works. Within the function, the scope remains. Every language has its own way of defining the scope, but in Python, it is safe to assume that it will be there within the function. Okay. Yeah, so yeah, that's it. So we have covered both access. Okay, now let's come to the complexity part. In this whole class, what is the complexity of access?
It's order of n.
Complexity. Access is O. Access and search. There are two operations. two functions defined. So tell me the complexity for both the functions.
Access1 search in.
Access1 search
In.
and good. Why access1? Because let's say I want to access element 0. Then it will directly fetch the element 0. It doesn't matter how big is your static array. And okay, that's how the Python implements it. And if I say I want to access the, let's say, 100th item, it will directly jump to the 100th item and will return you the data. So the access is generally O1 in Python in this list data type. And searching, as you can see, that you are iterating through all the elements. So if you have a large list, then the search will take large amount of time. So it's of order n. Right? It's the worst case scenario, right? In the worst case, your element will be found at the end of the list. So therefore, your upper limit will be of that order. Okay, does that make sense? Okay, let's now come to dynamic array. So what is a dynamic array? In a dynamic array, the size of your array keeps changing. Let me go back to my writing pad. Wait. Sorry, I'm actually work at home today, and I can't go to the lab. So therefore, I have some other devices to do the things. Okay, let's come to the second example now, a dynamic array. Can you see my screen?
Yes, sir.
Yes.
Do you see both my screens?
No, sir, just one.
Okay, great. Okay, dynamic array. In a dynamic array, you also want to add more entries. Let's say this array is given to you, this apple, boy, and cat, and I want to add another entry. Let's say a doll. What will I do? I will have to define a new function to add the entry. So let me call that function as append. I want to append, which means, let's say I have what was there? Apple, boy, cat, and I want to append. Maybe I should go back to my. Just a minute. Let me go to my code only. So let me define a dynamic array here. Let us define a new class, dynamic array. Okay, so fine, search is fine, data is fine. Now data will be I have to define new function called append, right? Which will append an entry. Let me say it will append an entry and what it will do is it will make it followed by whatever is the new entry, let's say doll. Right? How do I implement this? How do I implement this function? Append function. So it turns out that in lists, it's already implement it for you. You have self dot data dot append entry. That's it. It appends it for you. This is inbuilt in Python, right? Now, what is the complexity of this function?
O1. It should be O1.
O1. Yeah, makes sense. It should be O1. Append. It should be O1 because you just have to go to the last point and append something there. So it is O1. Good. Let's define another function here. Let's say instead of appending at the end, I want to insert something in the middle. Define insert, comma, some entry I want to insert at index or index I. Just I want to insert this entry at index I. What will I do? So basically, if I have, you may know that this is the way we write comments in Python. So let's say if entry is, let's say, girl, and my I is, let's say my I is 2, then my output should be what? Let's say this is my original value of data. Then if this is the operation I perform, what should be my outcome? 0, 1, 2. At this position, I want to insert girl. So it will become girl. Right? Now at the index 2, I have inserted girl and everything else moves to the right. Is that acceptable?
Yes, sir.
So how I do it in Python? It's already inbuilt, so we don't have to do much here. You just say self.data.insert. Somehow it is already inbuilt in Python, so we don't have to I, entry. This is inbuilt. We are not implementing it ourselves. That's it. It's done. The insertion is like this. And now, if you want to remove some data, define remove. Let's say you want to remove a given entry. Remove an item. Let me call it as target. So what you have to do is first you search for this and then remove it. Remove the first occurrence. Let's say. Right. So here what will happen is you first search for it and then remove the first occurrence. Right? And it turns out that Python has an inbuilt function for this called remove. Self.data.remove target. That's it. So, okay, I agree. Python already has it inbuilt, so we didn't have to do much. But in the next example, we'll see the cases where we have to implement all these things ourselves. But anyways, this was a good exercise for you to see how important functions are implemented. Okay, tell me now the complexity of insertion. What is the complexity? You want to insert something.
Insert.
Yeah.
One.
Order of 1.
One. Order of 1.
Yeah. Yeah. It can be taken as order 1 here. But imagine a case, let's say I ask you to insert something at the beginning, and then you also have to, what is done here is, okay, let's say in this it is not clear, it is kind of hidden how Python is doing it inside, we don't know. But one of the implementation could be where it is creating a new array, and it is no, what do you say? Yeah, it is creating a new array where it is inserting the first element here and then copying other elements to the next kind of, what do you say? Let's say I want to insert something here, then I will insert it here, and then everything has to be moved to the next item. Shifting. The shifting will take a lot of operations also. So let's say if I insert something in the beginning, then everything has to be shifted, which means n items have to be shifted. So n extra operations have to be done. So the insertion becomes of the order n. The complexity becomes of the order n. But of course, this is one way. There could be more efficient ways. And one of those ways will be, I'll be discussing next, that will be linked list, where you don't have to do the shifting. Like this is because of shifting. But if your data structure is such that you don't need to shift, then it will be order n, order 1, sorry. Okay. What about remove? Removing will be order?
It should be order n. It is also shifting.
Yeah. Yeah, because it is search also, right? You have to search first, and search itself is order n. Yeah. Okay, that was it. So this was about our dynamic array. Let's come to a next data type, which is linked list.
Sir,
Yes.
one thing in regarding that searching inside the remove option, is it necessary that it has to be that kind of linear search?
Yeah, if your data is ordered in some way, then you can use, as we discussed last time, the binary search, right?
Yes,
You go to the middle point and then half. Yeah.
Then the order, not necessarily it will be order n, right?
Yeah. Yeah. Yes. Yes. Correct. If it is sorted or some kind of organization is there in the data, then it will be, it can be made more efficient. Yes. Good.
Sir, but even in that case, we have to shift each element to left, right? After removing the target.
Yeah. Yes. Correct. Correct. The shifting will be again an issue there. Yes. Here you have search plus shifting. Okay. Okay, now I have to explain the next topic, which is a linked list. So I think I can go to my writing pad.
Sir,
Yeah.
can we say that the complexity of insert is order of n minus I, where I is the ith index we are inserting at?
Good point. Good point. Can we say it is O n minus 1? I n minus I.
That is a constant, so it will.
Yeah.
Okay.
I basically, you take the worst case scenario, right?
Yeah.
For finding the big O notation, you find that you take the worst case scenario.
Okay.
Let's come to the next topic called linked lists. So what are linked lists? These are also linear data types. Here, you don't have the problem of shifting. You don't have to shift the data because all the data is kept in the form of a chain. A linked list means a chain. So you have some data here. And this data points to another data data holder, and this points to another data holder or a node. In this way, it can keep going. This is called a linked list. So in for example, you had the example of apple boy. So you will have apple inside one node. Let's say this is called a node. And you have apple. Apple points to boy. Boy points to cat. Or basically boy points to a node which contains the data cat. This node points to another node which contains the data doll. And this points to nothing. It's nothing. Okay, this is called a linked list, right? Why are they used? They are very efficient when you have. So okay, tell me, with whatever we have already heard, they're very efficient in one thing. What is that?
Insertion deletion.
Yeah, basically because you don't have to do shifting here, right? No shifting, right? You don't have to do shifting. No shifting needed. You want to remove an entry. So how will you remove one entry? You want to remove this entry, just remove it and link it to the next one. That's it. You don't have to do any shifting. No shifting is required. Right? So let's discuss the nature of this node, which we call as node. The nature of this node is like this. The node So node is something like this. It is a container and it has a pointer to the, this is a pointer to the next node. And this is the container, and this is, there is some data inside it. It has data and a pointer. How will you define it in your Python notebook? Class node, right? And you will say define init self, right? And it contains some data, self.data is equal to, so what is that data? You can pass it as an input in the function, right? Oops. And then self dot pointer, or which basically points to the next node. You can say it is none. And you can initialize it as none. Later you can set it to something else. Similarly, you can initialize data also to none and set it to something else later. But anyways, because something data is something readily available. We don't know what is the next data node, but at least the data is immediately available. So in this way, I can define my node. Is that clear? Does that make sense? Yes?
Yes, sir.
Okay, now let's see how we will do all those operations which we have done earlier. Okay, tell me first one question. Is it a static array or a dynamic array? It can be used to implement a static array or dynamic array.
Dynamic.
Yeah, dynamic, because you can quickly add new nodes and remove the old nodes. So it is a dynamic, it is a way to implement dynamic arrays. Okay, let's now look at some of those things which we saw for the dynamic arrays. We can access elements, we can search for elements, we can insert new elements, we can append elements, we can delete elements, All those things are possible, right? Let's look at first one example which we will be using later. Let's say there is a classroom and there are students sitting. First of all, Hari is sitting, and then after him, Suraj is sitting. After him, some Ram is sitting. After him, Sita is sitting. After him, after her. Okay, in this way, you in a class, you can have all these people sitting in the classroom. Now, I can ask the question, first of all, is Suraj sitting in the class? What is the kind of problem it is? Is Suraj sitting in the class?
Sir,
Search problem.
That's up.
Then I can ask, who is sitting behind Suraj? Who is sitting behind Suraj?
Index problem.
Huh?
It's index problem.
Yeah, it is search plus indexing, because first you have to find Suraj and then you have to find who is sitting behind him. So search plus indexing. Search plus indexing. And if I ask you who is sitting on the third bench?
access problem.
Yeah, access, you can say access problem. Yes. Search plus access. Yeah, basically indexing means access only here. Yeah, and then if I ask you, okay, now a new student called, give some name, Rama, something. Rama enters the class and she sits at the back. Then we have to update the whole data structure, right? So what is this problem called?
Append.
Append. And let's say, yeah, in this way, okay, basically this is an example. Okay, so let's try to implement the whole thing using our data structure, our knowledge of Python. Okay, let's try to, so okay, we have defined we have defined nodes. Now, how do we connect these nodes to make a chain or a linked list, right? Should I go to my Python notebook? Okay, let's go to Python notebook now. Okay, so where are we? Like linked list. So first we have to define the node. Okay, I define a class node, and here I say initialize the class, self comma some data, and I say it has two entries, self dot data, which is, see what I have done here is this data is available only within this function, but once I attach it to this self dot data, then this is visible in within the entire class now. And self dot next is equal to none, right? The pointer. This is my node. Anything else needs to be defined? No. Okay. Okay. Now what I need to do is let's make a list. Let's make a singly linked list. Class singly linked. Okay, why am I calling it singly? The reason is that it only points in one direction, right? I think this will be clear later. Let me define. So what do you have here? Here we have two things which are available to us. One is where does the list start, and the other is where does the list end. It's called the head and the tail. So in order to initialize my singly linked list, I need a single node. Let's say it is Hari, right? And I will say self.head is equal to node, self.tail equal to node. So if you see, okay, when I defined my Hari points to, what was it, Suraj points to Ram, points to Sita. Here, my head is Hari. And basically my head is here. And this is my tail. The head of the list and the tail of the list. These two things I store. And as I am appending more entries, let's say if I add here Rama, then my tail will move to Rama. My tail will move here. Let me call it as tail. Does it make sense? Does that make sense?
Yes, sir.
Yes, sir.
In singly linked list, what you keep track of is the head of the chain and the tail of the chain. Now let's start defining different functions for access. Let's first do the operation of access. Define access. What do I do? What do I give as input? I give the index I, right? So basically this function, what it does is, it will say return the data or return the node, because once you have the node, you can access data, or you can get a handle of this, and then you can also find the other subsequent values. Return the node at index I, right? What other functions are possible? I'm not implementing it yet. What other functions are possible? Access, and then search, yeah, self comma some target value, right? Basically find if target is present in the list, or in the list, basically, right? I give error, so I will just add here pass so that it does not give error. That's it. Define. What else? Search, append, yeah, append is possible. Append self comma some node which you want to append. Append node at the tail, right? What else is possible? Insert, yeah, insert is possible. Self comma node at index I. So which means your, let's say it was earlier this, and if I do node equal to, I want to add Kamal at I equal to 1, then what will be my output? At 1 it will be Kamal, right? Right?
Yes, sir.
This is called a singly linked list. Now this is the abstract structure. Now you want to implement them. How do you implement? Let's start with accessing. So how will you access the ith element? Let's say I is 2. I want to know what is the data as data at 2. What will you do? Yes.
Start from head and move in I times.
Yes, very good. Very good. So start with head. Start with head. You will say my current node equal to self dot head, right? This is my current node. My current node is self dot head. Now I have my node is pointing to this, right? Now I will say node dot next, right? Now for j in range I, right? I will do I times shifting. And what is the shifting? I will just say node equal to node dot next. You remember, no, if you want to move to the next node, you have to use node dot next. Oh, did I introduce that in a class? If you want to access the class variable, then you can access it in this way. Maybe you might have seen in the lecture videos, the Python videos, but yeah, let's say you define a class. We have defined here, static array. I want to access data. I can say here. Yeah, a dot data, then basically it will give me self dot data, right? It returns the entire thing. Okay. So here, okay, you can also access, let's say, a function. If I can say a dot search, oh, that already I have shown. Okay, now here, where are we? In the singly linked list. When I say access, node dot next. Yeah, this is done. Return node, right? Is that all right? Should we try it? Let's define a singly linked list. Let me call it SLL equal to a singly linked list. SLL is a singly linked list. And oh, we have to initialize it with some node. Let me call it as that node as, let me make it more explicit. I will say my node is equal to, here I have a node and data. Data is Hari. And singly linked list with a node, right? That's done. Oh, but unless I implement append, how can I add more entries here? Okay, let us implement append also. Yeah, we have to implement append. Okay, let's do append first. How do you append an entry into the chain, into this singly linked list? I want to append another node at the tail. How will I do it? Yes?
Tail dot next equals that we can do.
Yeah, basically, your head will stay the same. You go to the tail, right? And then you take the new node. Now this node pointer should point to that new node, and this tail should point to the new node, right? So your self dot tail, the node which is currently the tail, it should point to the node now, right? The self dot tail, the tail should point to the node, and now this pointer self dot tail itself should point to the node. Are you getting it? Can I draw it? Okay, let me draw it. But this means I have to share the screen with you. Okay, how do I do it? Just a moment. Share content, screen, start broadcast. Um, So let's say you want to append something. So what you do is you have Hari. Let's say right now you only have this, and your head is pointing here, and your tail is pointing here. Now what happens? So, well, okay, let me draw it.
So I can see the black screen.
What do you see?
Now it is the black screen.
Yeah, black screen, yes. So I'm writing on the writing pad. So my head is pointing to this node, my tail is pointing to this node. Now I want to append a new node. So what will I do? First step is, okay, I have a node. First of all, I create a node, right? Okay, where is it? First of all, create a node, right? I created the node, let's say Ram, right? Now what you do, first, this was the first step, create the node. Second, this node, Hari, should point to Ram now, right? The old tail node should point to the node now, right? The new node, right? Which means this pointer, which was earlier none, right? Earlier it was none. But now it should point to this one. This point to none, right? And then third step is the tail pointer should point to the new node, which means this one, this should go away and it should point here, right? So that your new data structure will be like this. Your new, what do you say? Your new chain will be like this. Hari, Ram, and this is none. This is your head. And this is your tail. Right? So that's what, is this clear? Is this clear?
Yes, sir.
Yes, sir.
If conceptually this is clear, then implementation wise, I will tell you. Implementation wise, it is like this. Let me go to my, yeah. So I'm saying so first thing was create the new node. Okay, that we don't have to worry because the node is already given to us in the function. Second is the old tail node should point to the new node now. So this is the old tail node, self.tail. Now this dot next, this node should point to the new node now. And this pointer tail should also point to the new node now. That's it. Let me call it as new node to make it append new node at the tail. Then maybe that makes things better to understand. Right? Is that clear? Let's test it if it works. Here I say, oh, okay. SLL dot append a new node. This is a way I can, instead of defining it separately, I can define it here itself, right? So it has done it. How do I check it? I can say SLL dot head dot data, it is Hari, and SLL dot tail dot data, it is Ram. Does that make sense?
Yes, sir.
Can we make another function to print the entire thing? So let me call it as define print. Oh, but print is a standard keyword. Let's not call it print all something. Print all. So what it basically does is it prints all the entries. So it will say let's start with the head. My current node is self.head, right? And now what I will do is I will apply a loop while node dot next is not none. Until it is there, then node. So first of all, print the node data, print node dot data, and then go to the next. Oh, okay. We are printing the current only. So if while node is not none, right? Because when it will become node.x is none, then it will stop. Okay. Right? Does that work? Will that work?
Sir, node or node.data while node.data is none.
Data generally will not be none, but the pointer will be none. The next pointer should be none, no?
Okay. Okay, sir.
Because generally we are saving the data every time, but only when the chain is broken, when there is nothing at the end, means when it points to none, which means the chain has terminated.
Okay.
So let's do here SLL dot print all. Yes, it prints everything, right? And if I append something else also, it will print. Oh, Suraj, something. Okay. See now, everything it is printing. Oh, see there is just a formatting thing which I can do is I can say this. At the end, don't insert a new line, but insert a comma here. Now you see everything is followed by a comma, right? And then at the end, you can say print blank, which means it's just a new line. Okay. Yeah, so okay, this was our basic structure which is available. Now what can we do? Let's try to implement other things. Okay, is this let's come back to this function which we are implementing. Should we test it now? Access. Fine, access. I will say SLL dot access 2. Okay, it returns the node. Okay, it returns the node. Let's say I want to see the data of that node, Sita. That's correct. Hari, Ram, then Sita. So this function is working correctly, right? Are you happy with this function? Yes. Am I audible?
Yes, sir.
Yes, sir.
But this function has a problem. Let's say I put here 20. Error. The none type object has no attribute next. Basically, it is going next, and I have given index 20, and the chain is of length 4 only. So therefore, it has run into an error. How can we avoid that error? How will you rectify this error? Let me remove whatever has not been implemented.
If it is out of range, then we can return some integer.
If it is out of range, then we can return some integer. Yeah, but how will you check if the range is over?
I mean, after the for loop, if j value is exactly greater than I, it is going to be inside.
So once node is none, then we should terminate the loop.
Yeah, yes. If node is none, then break the loop, right? And return none basically. Right? It will return none. Let's see how it works now. Oh, acha, because it is none, therefore it has no data. None. Basically, this it returns none. You can do whatever you want here. You can also print a message here that print I is more than the length of the list, right? Now see, you get the message here, right?
Yes, sir.
Okay, this is fine. Now let's do search. How will you search things here? Let's implement search. Find if the target is present in the list. How will you do that? Okay, I'll leave it to you. You can implement it yourself. It's a very simple thing. You have done search before. Basically, you have to go over each element and find, well, let's say this is my target. Let's say my target is Sita. Then you will compare Sita with Hari. Okay, are they same? No. Go to the next one. Are they same? No. Are they same? No. Are they same? Yes. Now return this node. And if towards the end also you don't find anything by the even if in the entire list you don't find anything, then just return -1 or maybe none, right? Okay, let's come to this part. This is a bit tricky. Inserting something at a different at a given I. How will you do this? Okay, do it and give me the answer. Tell me the answer to this. How will you do this? Let's do it in 2 steps. First step is tell me the algorithm. Secondly, implement the algorithm.
So starting from head, we will move I times. Then at that node, we will insert the new node, and then new node pointer will be made to the.
Okay, move I times, and then
that node will be pointing. First, we will copy whatever the new node next node is. We will copy it somewhere. Then we'll insert the new node at that point, and then that will be pointing to the copied node.
First, we will make the ith node point to the new node which we want to insert, and then the node which we want to insert, we will point the pointer of that node to the node where we broke the link.
Yes, right. ith node should point to
the new node which we want to insert.
So shouldn't it be I
yeah,
minus 1th
I-1th node is good. I-1th node should point to the new node. Okay, then
new node should point to the I+1th.
New node should point to the
I+1.
I+1.
basically the old ith node.
Yes, old ith node.
Yeah, that's it. Yeah. Okay. Let's implement it now. So first of all, you have to move I times. We already have something to move. This function is already there, right? We can directly use it, right?
Yes, sir.
We will do my current node is equal to self dot access what I, right? My access will give me I. Okay. Then what next? Move, not move I times, move I minus 1 times, right? We want the I minus 1th node. Because if you go to I, how will you come back to I minus 1, right? Does that make sense?
Yes, sir.
If you go to I, coming back to I minus 1 is not possible because it is only pointing in one direction. So therefore move I minus 1 times, let's say I is 2, then only move 1 to 1. And then from here you do the things. Okay. So first access I minus 1. Okay. Now your node is pointing to the I minus 1th node. Okay. Let me put it. Okay. Then what will you do? Then your node should point to the new node. Node is equal to new node. Now, how will you do? Node dot next equal to new node, right? Then
New node dot next.
New node dot next equal to what?
Equals to new node plus 1.
New node plus 1. What
New
is that?
node I.
Sir, actually, before assigning new node to node dot next, we should copy it somewhere. Otherwise, it will be lost.
Yes. So what we do is, okay, instead of copying, I'll just do it before. New node should point to the ith node. Did I do something wrong? New node dot next equal to node dot next, right? Right. So the old ith node, which is this is the old ith node, right? Node dot next. Node is the I minus 1. Node dot next is the ith. Are you getting it?
Sir, can't we also write here self dot access I?
Okay. Yeah. Yes, you can do self dot access I, but that means your algorithm will be, what is the complexity? You are traversing the whole thing twice, right? You are increasing your number of operations unnecessarily.
Okay.
You want to write efficient codes that with minimal operations you cannot achieve your goal. If you do it many times, then yeah, it will become inefficient. So here, okay, I went up till I minus 1. Okay, let me see. Okay, this is okay. I Kamal. Then I in this example, else I want to insert at Kamal, a Kamal at Suraj. So I will go up till here only, and then this is my node. My node points to this is a new node. Sorry, my node points to Hari. Then I'm saying now my node points to Hari. So let me write it down now. Node points to the Hari node. Then let me just write it like this. It means that the Hari node basically points to the node which contains Hari. Now node points to Hari. Now the new node should point to the old. Now new node dot next is node dot next. What is node dot next? Node dot next is Suraj. Okay. So my new node dot next also becomes Suraj now. Then node dot next is new node, which means I'm saying my node dot next is new node. My node is Hari. So this is now Hari points to new node. Hari, instead of saying node is Hari. Let me write this Hari node just to make it. So here node is Hari node. And then after this step, my node dot next is Suraj node. And here my Hari node points to new node, right? Yeah. Does that make sense?
Yes.
Okay. Will this code work for every case? Is there some case which is not covered by this, what we have written?
Sir, if I is greater than the whole length of list.
Pardon?
At the tail.
At the tail, okay. What will happen at the tail?
At the head.
At the head, what will happen at the head? Yeah, at the tail, nothing will happen because see, if I want to insert something at the end, so what will happen is it will access the I-1, which means let's say Sita, it will access Sita. And then same thing will happen. The new node will be inserted here. So nothing will happen. No problem will happen. This code will be able to handle that case properly. But the problem will come when my I is 0, which means my I is 0 means my I want to insert things at the head itself. When my I is 0, then I-1 will not exist, right? When you say self.access I-1, self.access -1, that will give you an error, right? So here you have to insert a condition if I is greater than 0, right? And if I is less than 0, oh no, it cannot be less than 0. If I equal to 0. Okay, if I is less than 0, then definitely I say else if I equal to 0, then do something else. Of course, if I is less than 0, then it will be if I is less than 0, then so you will return or you will print, just print I should be greater than 0, and you return something. I don't know, some error you will return. Or actually, instead of doing this, what you can do here is, this is a Python trick which you can do here. You can say assert I is greater than 0, greater than equal to 0. And if this condition is not met, then you say I should be non-negative. Okay, so anyways, this will handle that case. It will just throw an error. It will raise an error. You want to see what happens? Okay, let me. Let's do, what is it? We are doing insertion. SLL.insert. What is the format? You have to first the new node. Let me call it as node Kamal at position, let's say -1. it raises an assertion error. I should be non-negative, right? It gives you an assertion error. This is because of this assert function. This assert function gives me the assertion error. Okay, fine. Oh, where are we? Yeah, this is done. Okay, let me insert it at 1. Yeah. Let's do SLL dot print all. See, it now becomes, oh, maybe it inserted. Why it inserted twice? Okay, maybe I ran it twice. Okay. Okay, so yeah, it works, but it will not work for 0. Or if you want to work 0, 1, 2, 3, 4, it will even work for 4, like 0, 1, 2, 3, 4. It will even work here. See, it will not work for 5 for sure. It will give an error here that none type has. So you can do some error handling and make it an intelligent message. But anyways, here I'm leaving it like this. Let's say 0. See, it did not do anything. So, okay, we have to write this case. What will you do? Okay, tell me now, what will you do when I is 0? Yes? What will you do when I is 0?
Self dot head is equal to new node.
Self dot head equal to new node. Okay, then now
So-
your head is pointing to the new node. Now where will the new node point to?
New node will point to tail.
Tail may be at the end.
Okay, at the end.
Sir, first
No.
new node will point to new node dot next equals head, and then we will do this.
Yeah, so first my new node dot next should point to head, right? That means whatever was the node, currently the head node, and now my head will point to the new node, right? Let's try it. See, it works now. Now you inserted Kamal at the head node. Okay, I think that's it. So this was, so now why is it called singly linked list? Because you can only go in one direction, right? Your node is it links only to the next. But let's say if I have a doubly linked list, then I will define my node in this way. It will also point to the previous self dot previous. So basically it points to, it points in both the directions. Let's say you have reached I, you want to go to I minus 1, you can use the previous link to go to I minus 1. So this becomes little more efficient if you want to do traversal in both the directions. But singly linked list is efficient for traversal in single direction. Right, this is for a doubly linked list. Anyways, we will discuss that in the next class. Okay. For now, I will stop here. Is this clear? Do you have any questions until here?
Yes, sir. Sir, in C language, self dot next is basically a pointer, but in Python we don't have pointer. So what is exactly this self dot next for whatever node we are talking about?
It's a reference. It's a reference to the class node or the instance of the class node.
Reference as in address or what?
Yeah, it's address basically. Yes. Address. Yeah. So here in Python, we don't have the concept of pointers, which is very much there in C, C++. Here we have only data and the address. Okay, so if that is done, should we stop here?
Sir, are next and
this-
previous function already defined?
Where? In the doubly linked list?
Yes, sir.
See, this is not the list. This is just single node, right? A node has got just connections or the pointers. So this will point to the next node. This will point to the previous node. This is just, you can say in a chain, there are links. So this is a single link in the chain. This is not the chain. This is not the complete chain. This is a single link in the chain. And it has a provision to connect to the next node and another provision to connect to the previous node. Does that make sense?
Yes, sir.
Okay. Fine, then we stop here.
Sir, please share this notebook file also with us.
Sure. I will share. Thank you very much. Bye.
Thank you, sir.